All right. The moment you have been waiting for, I am going to go through this very exciting quiz practice. These formulas for magnitude, direction, dot product, kind of how to transfer from linear combination to component form, and then this is polar. That is on there. Here it's starting with polar, where you know the magnitude and the direction, and then you are getting the x and the y component, which is kind of the word problem deal. This is that how to find the angle between these two are kind of related, and so you would use whichever one is most handy. Straight up finding the angle, you would want to be leaning towards this and just doing cosine inverse. Just need to be careful with your parentheses and such, and then obviously unit vector. So those are going to be on your actual quiz also, so those are not things you need to know off the top of your head. You just need to know what they are, when to use them, and so on. So I'm going to go through this pretty fast, which probably means I'll make mistakes, but I'll try really hard not to. So use the vectors blah, blah, blah to find the following. Show your work and your setup. Okay, I will. So I'm supposed to take R, and then I'm supposed to subtract 2 times S. And I am going to actually do this first and then change this to addition. So I'm distributing that negative. And then I'm going to add them together by combining the 2 x components through addition and combining the 2 y components. So hopefully I didn't do anything stupid there in my haste. Then in this next one, it's asking me to do a dot product first. And the reason it's first is it's inside the parentheses. And then that will actually turn out to be a number, as dot products do. And then I'll be multiplying that by a vector. And so my answer in this case will be a vector. So if I take S, 5, 3, and I do that dot product of S and U, not you personally, but vector U, that's going to give me a number. How does that work again? I'm going to be taking the x coordinate of each, multiplying them together, and then adding the product of the y's. And so here I'm going to have a 30, here a -9, so altogether 21. So this turns into 21 times vector r, which is -2, +2, and that would become, I'm just basically distributing that 21, so -42, +42. And you want to make sure you're using proper notation, whether you're in polar form, coordinate form, or whatever it might be. Here it looks like I'm going to be adding R and U first because that's in parentheses and PEMDAS is real. So R plus U is literally taking these x and y components from R and adding them to the components of U. So when I add the x components, I'm going to have a 4. And when I add the y components, I'm going to have a -1. And then I'm going to be doing that dot product or multiplied by 5, 3. So this one's actually going to give me a number answer because that's what dot product does. So I take the x parts of each vector and multiply them and then add it to the product of the y's. So I'll have 20 plus -3, and I'm getting 17. So my answer is just a scalar, a number, so no notation necessary in terms of brackets or anything. Here I'm looking for an angle between, and since I'm straight up looking for the angle, I'm going to go ahead and use this formula where I do the cosine inverse. I'm actually going to scoot that out of the way because I need a little more space. So I'm going to be taking the cosine inverse of dot product, so I need the dot product of R times S. So looking up above, I'm going to have this times this, which is going to result in -10 for the x pair plus 6 for the y pair or coordinates or components. So I'm getting -4. So R dot S, my top up here, is going to be -4. Now I need to find the magnitude of r and the magnitude of s. So I'm just Pythagorean theorizing it. I'm not going to include any negatives because they'll just mess me up. So I'm going to get the square root of 4 plus 4, which is 8. And in real life, I have to rationalize that. But here I'm just typing it all into my calculator so it's easier not to. So far the pieces I need are my dot product and that one magnitude. Now I need the other magnitude. So looking back at vector s, that's my 5 and my 3. So I'll have a 5 squared plus 3 squared. And so I'm going to have 25 plus 9. So I'm going to have root 34. And again, it's important that you know how to enter all of this jibber jabber into your calculator to kick out the right thing. Also important to be in degree mode. So inverse cosine -4 divided by, and then in parentheses, the square root of 8 times, the square root of 34. And then just kind of make sure you're closing out all the parentheses you opened. And if you do that properly, you should get about 104 degrees. And keep in mind, you could kind of sketch these and see if it makes sense. So here's me up here. R is -2, +2. So this is vector R. And then vector S is 1, 2, 3, 4, 5, 1, 2, 3. So then this is vector S. So this is theta. So 104 makes me happy because that seems logical given the drawing of the two vectors. Find x so that the vector x18 is parallel to. Okay, so parallel to means that they are multiples, or that there is a multiplier. And so you have to look at the pair that you know. So to go from here to here, what happened? The quantity over here on this side got divided by a -6. Or if you want to think of it going the other direction, the -3 got multiplied by a -6. So you have to have that same multiplier. They have to be scalar multiples of one another. So the easiest way to do that is to say, well, then I would need the 12 to get multiplied by -6, making that x a -72. And that works left to right, because if -72 were divided by negative, where did I get a 12? Oh, right. By the -6 right here, I'd end up at 12. So however you want to look at it, left dividing in order to get the smaller numbers, or the right side multiplying, but they have to be scalar multiples. And so what's happening is this first one, if I make that a -72/18, is getting divided by -6 to become this other one, and that will make them parallel. So the x value that I was missing has to be a -72. Here, I'm trying to make them orthogonal, and you need to know that that means they cross at 90, and that means dot product equals 0. So I need the dot product to equal 0. So that would be 9 times -2 for the x's, and then plus y times 18 for the y components has to add up to 0. So you can have -18 plus what times 18 will equal 0, and your answer is going to have to be a 1. The other way to think about that is slope. Here the slope would be the y over the x, which would be a -9. And if I want them to be orthogonal, which we used to call perpendicular, then I need this one to have a opposite reciprocal slope. So when I'm looking at y over 9, I would need that to come out to be a positive 1/9 in order to be opposite reciprocals with the other one. So technically the dot product equaling 0 is kind of what you want to be familiar with now and be able to show that setup, but you can kind of check it in terms of slope and make sure that you are doing that accurately. All right. So now what are we doing? Vector u has an initial point at -3, +4, and a terminal point at 1, -5. Sketch u and then write it in component form. So I'm looking for the x and the y component. So the initial point is at -1, 2, 3, up 1, 2, 3, 4. And then the terminal point is at positive 1 down 1, 2, 3, 4, 5. And I'm going to be going from initial to terminal. So make sure that you pay attention to that. So that is my vector u. And to get the component form, remember we basically treat this as x1, y1, x2, y2. And our vector is going to be the second x minus the first, the second y minus the first. So this turns into a 4, and this turns into a -9. So that is going to be my component form, but then you also should look at your sketch for verification, because this means you're moving 4 to the right and 9 down. So go back over there and see if that's actually what's happening from beginning to end. Am I going 1, 2, 3, 4 to the right and 1, 2, 3, 4, 5, 6, 7, 8, 9 down? The answer is yes. So then I feel pretty happy. When it says to show your work and to kind of your setup, this is all I'm looking for, and then it should just jive with your picture. Okay, so here, this is my initial point, and this is, oh, interesting. Okay, so this is the actual vector and component form. I have the initial point, but I'm looking for the terminal point. So if you think about what that means you're missing your x2 and your y2. So you can kind of treat it like an equation. You would say, okay, here in the x spot, I have a 7, which came from my second x minus this first x in the initial point. Then in the y component, or the y spot, I have a -3 from right here. And that came from whatever y2 is minus my y1 value from in the initial point. So if you look at this equation, your x2 must have had a value of 10 in order for that statement to be true. And this will turn into addition. So the only way this statement is true is if the y2 value was a -8. So that other point, and it is a point, a terminal point, so I'm using parentheses. This is the second x and the second y. So I would have an x value of 10 and a y value of -8. So it's the exact same concept as the previous 3A, but it is kind of thinking backwards. This is the part of the video where I start to choke, like always. Okay, what are we doing next? Unit vector. That's so cool because up here, I have a formula for that. I need to take the initial vector in component form and divide it by its magnitude, which makes so much sense because a unit vector is 1 unit long. So I'm taking the vector and dividing it by how long it used to be. Because if it used to be 5, I'm going to divide it by 5 so that it'll be 1. So let's do that. Let's take our initial vector and let's divide it by the magnitude, which means I need to find the magnitude, which means I'm going to show my work because I like full credit. I'm going to ignore the negatives because they would go away anyway while I was squaring. And if I don't ignore them, I might mess it up on my calculator. So this is turning out to be root 65. That's lovely. It's not a perfect square. It doesn't contain any perfect squares. I can't use a decimal. So here's where I'm at. Finding the unit vector. Okay. So keep in mind that that means I would have to put the x component over the magnitude and the y component over the magnitude. But we are in honors pre-calc, so I also am responsible for understanding that I would need to rationalize that denominator in both cases. And I'm winning right now in the messy writing department. So hopefully you can see what that is all about. Okay, now we're finding a vector of magnitude 6. So instead of being 1 unit long, I want it to be 6 units long. But to go in the opposite direction, I'm basically going to take my unit vector and I'm going to multiply it by -6. Because if you remember when we talked about having a specific magnitude, you have to shrink the vector down to 1, so it's 1 unit long, and then you multiply it by the number you're trying to get it to be. So if you want it to be 6 long, you multiply it by 6. But if you want it to be 6 long and go the opposite way, now you need a -6. So that's our k value, or our constant, that we're going to multiply by the unit vector of n. Thankfully, I just found the unit vector of n right here. So that's handy dandy. So what I'm going to be doing is taking that unit vector that I found, which was relatively ugly, but whatever. Looks are not everything in the vector world, or the real world for that matter. And I'm going to multiply it by -6. So I'm really just distributing. So this turns into 24 root 65 over 65. And then I know that I need to check those outside numbers and see if they reduce, but they don't. But yours could on the real quiz. And then here, I'm going to get 42 root 65 over 65. So in 4a, I made the vector 1 unit long. And then in 4b, I made it 6 times that long so that it would have a magnitude of 6. But I also used a negative only because it said to go in the opposite direction. Okay, converting. So now up here, I had some conversion stuff right here and right next to it, kind of depending on what I was converting to and from. So let's check it out. Converting kind of feels like something you should do in green. So this is linear combination. It is the same as a -2 for the x component and a -5 for the y component. But it wants it in polar form. So Scoochie up here with me, we started here. I just wrote it like that because that takes no brain cells, which is about how many I have at this point. And then I now have to do this little trick to it. So I'm going to turn it into polar form. I'm going to find the magnitude and the direction. So I know how to do that. I'm going to go, because keep in mind, this is r or magnitude, and then I'm going to find the theta by using the tan inverse. Let's think for a minute though. This is going to go 2 left down 5. It's going that direction. So that means when I go to do my tan inverse, I am not going to get the right answer. I'm going to get an answer over here. It'll be positive, but I'll need to add 180 degrees to the calculator answer in order to be at the right angle. Okie doke. So let's go ahead and find that magnitude because this is nothing more than a new way of saying r when we did polar. So the magnitude is going to be the square root of 2 squared plus 5 squared. So I feel like that's root 29, and I'm going to leave it like that because that is the most accurate. And now that I'm doing polar, I have to write it with brackets rather than the vector notation when I did components. So this first thing is going to be the magnitude of that angle, excuse me, of that vector. Now I need to do my tan inverse, and I'm going to do tan, this is to find theta, inverse of my y over my x, which is going to turn into positives, but whatever, you can enter it however you'd like into your calculator. You can use the negatives. They'll cancel out on your calculator as well because your calculator is really smart. Okay. So I am getting 68.2 degrees, and I'm giving that a sad face because that is exactly the opposite of where I want to be. So that's where I need to be smart enough, and I like to think about it ahead of time because I won't think about it otherwise at this point, and I need to know to add that 180 based on the fact that it was pointing down towards that third quadrant. So then my angle's 248.2 degrees, which does fall into the category that they gave me, which it's hard not to because that's in the circle. Okay, more converting, but now we're starting with polar. So zoom back up here, and that puts us in this scenario right here. This is polar, and I'm going back to like what we did last time, r cosine theta, r sine theta, except our new r in our picture is the magnitude. So let's go back and do that. That's pretty easy. We've done it before. There's no tricky bits about what direction it's going. But think about this. If it's going 57 degrees and out 1, 2, 3, 4, you should probably end up with coordinates that are both positive because that's in quadrant 1. So I like to use that as a check on whether my answers make sense. So my x component for component form is going to be my magnitude, which is this guy, times the cosine of the angle. So 4 cosine 57, 2.18. Okay, then what about my y coordinate? I'm going to be doing 4 times the sine of 57. And I'm coming up with 3.35-ish. Okay, well, you only went out 4 this direction, so it makes sense to have 2.18 here and 3.35 here because Pythagorean theorem and life in general tells me that hypotenuse has to be the longest. So I needed 2 answers that were less than 4. So I'm writing it in component form, which means that I have a Vx and a Vy. So I'm using my little vector type parentheses. So I'll have 2.18 here and 3.35 here. And I feel pretty happy because they're both positive and they would get me into quadrant 1. Okay, the grand finale. Now this looks like it has a zillion parts, but it's actually helpful, I think, because it's breaking it down into like literally every step that I have to take. These are always tricky. This is making me understand heading and bearing and tangent, and theta, which always starts over here on the right. So let's start with a little north, south, east, west. Or as you guys say, never eat soggy waffles. Okay, airplane heading. I feel like an airplane should be below. South 65 west. Okay, so that means I start at south and I motor 65 degrees over towards the west, and it's going 535 miles an hour. That, my friends, is the magnitude or the magnitude of the airplane. Okie dokie. But I actually need this in terms of theta from here. So I need the theta for the airplane. So think about that. If this went over 65 degrees, then in that quadrant, I'm taking my 90 minus 65 and finding out that that means there's only 25 degrees on this side. Why do I care about that? Because measuring from the starting line for theta, I'm going 180 plus I'm adding that extra 25. So the theta for the airplane is actually 250, the directional angle. So that's the first thing it's asking me for, and my answer is 250 degrees. One of the reasons that I'm breaking this down is, like, let's pretend you get this wrong. Well, you are going to now have every other question wrong. So I'm making you write everything separately so that if I see where you went wrong, I can follow your work from there and see if your answers are right based on your starting number that might not have been right. So it's hopefully going to help you along the way. Okay, now we're finding the vector representing the plane in component form. So we need a Vx and a Vy for the airplane. I'm going to actually do that up here because I don't have very much space. So the x component for my airplane is going to be the magnitude, which was 535, times the cosine of the theta that I just, oops, I meant 205. See, look at me talking about getting it wrong. I had like a dyslexic moment there, sorry. Times the cosine of 205. And I'll find my y component for the plane by taking its magnitude or speed times the sine of 205. I expect, given the position of my vector, that I'm going to have a negative x and a negative y because I'm in quadrant 3 with my airplane vector. So if I do my 535 cosine 205, that is putting me at negative 484.87. And when I do the same but with sine of 205, I'm landing at negative 226.10. Okay, does that seem right? That I would be going to the left, negative 480, and down to 26 to get that right triangle. Seems logical to me. So this is my x component and my y, both negative because I'm in quadrant 3. Makes me happy for the airplane. So you know that there's a wind coming because that's how these problems always work. And everybody knows that wind is purple. So my wind is 42 miles an hour. So that is the magnitude of my wind. This one is blowing at a bearing. And this teacher put a nice little reminder here for you that that's clockwise off north of 110. Okay, so let's go draw that. That means I'm starting at north. I'm going 110. So past, oops. What is happening, Notability? I'm going to start up at north and I'm going to go 110. So 90 plus 20. So I'm over here-ish. But keep in mind that whatever this would be, I need to actually do that over on the end because we do from tails to heads. So the next, like I'm taking this same concept to the end of the plane vector, starting at north, going 110, puts me kind of down here-ish, and that is only going to be 42 long. So I'm going to use the one I drew up here because it's easier to see. So up here, you can kind of get the more magnified version than this little dinky thing down here. Either way, I need to come up with the theta equivalent of that. So if that was a 110 degree angle that I just did, I went 20 past here, but I need to measure it as a theta. So you could either call it negative 20 if that makes you happy, or you could call it from the other side, positive 340. It will not make a difference on your calculations. So either way, you have to get a handle on like what is that angle measured from the zero line for theta. So all it's asking first is the wind's directional angle. So here an accurate answer is negative 20 or positive 340. Either one of those is fine because they are coterminal, and so they are samesies. Okay. So now let's kind of keep in mind what we're trying to find. This is what we're trying to find. We're trying to find the result. So that's really crooked, but whatever. So the blue was my original plane. This was my little wind. And now the red is longer than the blue. So I'm expecting a number for the magnitude eventually to be greater than 535. And as a theta, I'm expecting the angle to be a little bit further because the blue one stopped here and the red one you can see is a little bit beyond the blue one. So let's just kind of use that as a common sense guide for our answers. Find the vector for wind in component form. Alrighty, so the x component for my wind is going to be my miles per hour, which I felt like was 42, yes, times the cosine. Again, you can use 340, you can use negative 20, it won't make any difference. In fact, just to be rebellious and confusing, I'll use one of each. It does not matter. They are coterminal. So 42 cosine 340, I'm getting 39.47. And when I do, I don't want to do cosine twice. What the heck? When I do the sine for the second part, the y part, I'm going to have 42 sine of negative 20. And I'm going to get negative 14.36. So go back to your picture and see if that makes sense for this little dinky arrow that we have here for wind. It's in quadrant 4, so positive 39.47 and then down 14. So that actually makes sense. So my component form for the wind is going to be 39.47 as my x component and then negative 14.36 as my y. You know where this is going. Now I have to find the resultant. So I'm adding the plane to the wind now that I have them both, I should say, in component form. So I'm going back to part C and I'm going to take this x from the plane and add from part E the x coordinate or component from the wind. Now for my y's, I take the y that was the airplane only and I add it to the y component that was the wind only. Okay, so I'm taking negative 484.87 and I'm adding 39.47. And I am getting as my component for x, negative 445.4. Now I'm going to do the y part. So negative 226.1 plus negative 14.36. And I'm coming up with negative 240.46. So if I look at my red resultant vector, that still makes sense. It's negative for an x, negative for a y. So my component form to get here should have both those things be negative. But when I'm done, I want to be able to give my magnitude and direction. Now this one has a little tricky bit. It wants you to do it as a bearing. So let's first find theta. Well, actually, first, let's find the speed. And keeping in mind, I expect based on the length of my vectors in the picture, I'm expecting it to be longer or faster, I should say, than 535. So I'm going to Pythagorean theorize this whole bit. And so let's do a little mathing. So I'm getting 506. Maybe I drew my picture crappy. And maybe my wind went down too far, so that should have been shorter. But 506 is certainly a reasonable answer, and that's 506 miles per hour. Now, bearing, let's first find theta. And theta is going to be measured from the theta starting spot. But theta is the only thing I know how to find. And keeping in mind that I'm in quadrant 3 with this thing, I'm going to take whatever the calculator gives me, and I'm going to add 180 to it, so I can figure out what my theta is measured from 0. So when I do tan inverse of my y coordinate, and I'm doing the resultant over my x coordinate, I'm going to get something, something. Hang on. Okay, I'm getting 28.36, which would be over here. I'm going to add 180. And my theta is 208.36 degrees. However, this is asking for bearing, and bearing is clockwise off north. So let's figure this out. My theta was 208. So over here, that's 208.36. That's my resulting vector. That's where the plane is going with the wind impacting it. What I need is to figure what that would be as a bearing. So starting here at north and traveling clockwise. Okay, so that's kind of tricky. What I know is that from here to here is 180 degrees. So I need to be able to add this little mystery bit over here. So let's figure it out from the other end. The other end was 208.36, and I know to here was 180. So I'll take away my 180 from this answer, and that'll tell me that this extra piece was 28.4. And that'll help me find my mystery piece over here, because that is the rest of this 90. So if I do 90 minus 28.4, and there's a lot of ways to like noodle your way through this. I'm just showing you a way. I'm finding out that this is 61.6 degrees. So this is going 180 plus an additional 61.6. So if I add that 180, I'm coming away with 241.6 degrees clockwise off north to get to that same spot. And that's what's going to go in here. Boom. That's so much thinking. If you took the time to go through this and understand it, you're going to be super happy that you did. This is going to be suspiciously similar to the quiz, and I hope that it benefits you, because a whole bunch of snow days and days off prior to a quiz is stink bag. So I'm hoping this gives you a little leg up. See you soon. Ciao, babes.